Hi, my name is Josh Kahn, and I'm a Principal Solutions Architect at AWS focused on serverless. In our session today, we're going to explore opportunities to enhance reliability and add visibility to errors that you might encounter in your serverless applications. No matter how hard we try, how much we debug, errors are just bound to happen. Trust me, I've run into plenty myself. Maybe your application receives an unexpected input, or your developer accidentally introduces some erroneous code. Things happen. And this is an error message that I've run into more times than I care to count. If you're not familiar with it, you might see this internal server error come when you're using Amazon API Gateway and the downstream service, in our case generally a Lambda function, throws an error or returns a malformed response. In that case, API Gateway is going to return with this rather innocuous internal server error. Now, as a developer, that's a pretty hard error message for me to deal with. There's not a lot of detail here. For the end client, it's great. We don't want to tell the client too much about the underlying infrastructure and what might have happened that caused the failure in the application. But as a developer, unless I'm intimately familiar with the architecture, it can be hard to go troubleshoot an error like this without diving into lots and lots of CloudWatch log trails. Lambda can generate a lot of log messages, particularly at scale. And while CloudWatch has introduced a lot of great tools over the years that allow you to dig into those logs more easily, if the error message wasn't actually logged by the developer, or somehow the error got swallowed in the application, it becomes even harder, if not impossible, to find. In our session today, we're going to talk about how to add reliability to your serverless architectures. First, by understanding the automatic retry behaviors that are built into these services. We're also going to talk about the configuration options that are available for those retry behaviors so that you have better control over what happens when an error occurs. We're also going to talk about how to add visibility to errors within your Lambda functions by looking at the different invocation types that Lambda offers. The error handling approach and the configuration options are going to differ based on the invocation type. And we're also going to try to take an approach that minimizes developer impact. That not only means that our developers don't have to spend time building this into every single Lambda function that they write, but it also means that we're going to have more consistency in how errors are handled across the application. Please note that this is a 300-level session. We're going to be discussing architectural principles and also looking at code samples. This talk is not intended to be an introduction to Lambda or to serverless. We're also looking at just one particular vein of observability, which is visibility into errors. If you're interested in a more general approach to observability or a discussion of Lambda or serverless in general, there are some other great sessions available at re:Invent this year. So throughout the talk, we're going to use this very simplistic serverless e-commerce architecture to explore the different invocation types that are available in a serverless architecture. And for each one, we're going to talk about the error handling approach and configuration options available. So the first is a synchronous invocation. In this case, we have a mobile application making a web API type call to Amazon API Gateway. An API Gateway then invoking a Lambda function that writes to a DynamoDB table. Now in this case, the mobile application is actually waiting for a response to this operation. An API Gateway has a 30-second timeout. Your Lambda function needs to respond within that time because the client is waiting around for the response. It's synchronous. This, for those familiar, is also where you might see that internal server error message that I showed earlier. The second invocation type is asynchronous. In this case, we have Amazon EventBridge writing a message to a queue internally managed by the Lambda service, not your function. And when EventBridge successfully writes that message to the service, Lambda essentially responds with, "Hey, I got it," and EventBridge moves on. It's not waiting for your function to actually process that event or that message. So that's meaningful because the work is going to happen later down the road whenever your function is available and free to process and do the work. Again, it happens asynchronously. The next type of invocation is pull-based. And we're actually going to break pull-based invocations into two different categories. In both cases, the Lambda service, not your function, but the Lambda service, is pulling some event source for messages or records that need to be processed. In both cases, you're actually going to have records delivered in batches or groups of records, not a single event that your function will be responsible for processing. The first category of a pull-based invocation is streaming sources, typically things like DynamoDB streams or Kinesis. The second type, or the second category of pull-based invocation, is from SQS. And in this case, again, the Lambda service is pulling for messages on the queue, and messages are delivered in batches. The error handling approach and the configuration options available for those two different pull-based event sources differs. So we're going to break those out separately in the talk. The last item that's on the screen is AWS Step Functions. And we're going to spend just a little bit of time on Step Functions towards the end. But Step Functions gives you an incredible amount of flexibility and configurability right within the Amazon state language that you use to define your step function state machine. And you can define things like error handling and retry behavior right within the state machine definition itself. So let's get started by talking about synchronous invocations. And for each invocation type, you'll notice we're going to kind of follow a pattern of the information that we cover. First, we're going to talk about the retry behavior that's built into the system. Now, in the case of synchronous invocations, there is no built-in retry behavior. If your function fails for whatever reason, the client, in the case of our e-commerce example, the mobile application, is just going to get an error message. The client can retry if it would like to, but the service itself is not going to automatically retry. Now, we have a few goals for our error handling, and no matter the invocation type, these goals are pretty consistent, so we probably won't talk about them in depth for each invocation type. But the primary goal across handling all of these errors is to log the errors, and to log them in a consistent, structured fashion that allows us to generate things like metrics and alarms from those metrics. We also want to log the messages and the errors in such a way that we can derive insights from them, even at very large scale. And that allows our developers to easily determine what's causing an error and even build capabilities like error budgets to understand the service level of the services that you're managing and building. We also want to handle and return from errors in such a way that we can get useful tracing of our distributed system from tools like AWS X-Ray. That's incredibly important as you're building these serverless architectures, is to understand where the failure actually occurs. Now, particular to synchronous invocations, it's also important to return a sensible or sanitized type error message to the caller. There are going to be some types of errors that the client could actually try to recover from, versus others where there's a back-end code problem or configuration that the client frankly can't, even if it retries. So when it makes sense, we want to return an obfuscated kind of generic error message like internal server error. And in other cases, we might want to return an error message that indicates, for example, an item wasn't found in our e-commerce database. So we're going to differentiate between those two types of errors. The first category we're going to call client type errors, right, where a bad payload comes in from the client, or it's again trying to find an item that doesn't exist in the database. And the second type we'll call server or function type errors. And those are errors that the client can't recover from necessarily. That would be, for example, in our e-commerce architecture, if our Lambda function cannot write to the DynamoDB table, it doesn't have put item access or permission to do so, it's going to throw an access denied error. Your function also, you can only run so many concurrent invocations of Lambda functions in your account in a given region at any time. Anything beyond that will get throttled. And essentially, a throttle is an error as well. So we want to be able to report on those things independently. Again, for each invocation type, we're going to talk about the actual code that your developer would need to write in the Lambda function, as well as an approach for building centralized middleware that can be used across all functions of a given invocation type. And if you're not familiar with middleware, it's custom code that wraps the function handler. And that code can be called before and or after the function handler itself. And there's libraries that support you building middleware across all of the runtimes that Lambda supports. A popular one for the Node.js runtime is a library called MIDI.js. And it gives you a lot of flexibility to build some great middleware. So we're taking the approach of using middleware throughout this talk because, again, it kind of centralizes how you're handling errors, and it's going to be consistent across error types without your developers needing to do a lot of work. So in the case of our synchronous invocation, the Lambda function is going to need to differentiate between those client and function type errors. So in the case of a client type error, something like, a book wasn't found in our eCommerce catalog, it's going to throw a custom error type, right? Something like book not found error. And you might equate that with an HTTP error code in the 400 range, maybe 404 in this case. Any other type of error, like access denied, the function's not even going to try to catch. We're just going to let it bubble up and populate up to the middleware. So in that middleware layer, it's going to catch any errors or exceptions that occur in the Lambda function handler itself. First, it's going to grab that error and log the error to Amazon CloudWatch using something called embedded metric format, or EMF. And EMF is a capability that was launched not all that long ago that enables ingestion of data in the form of log messages and generate metrics from them. Now that's a lower latency and lower cost approach than you might have found historically in using the put metric operation. So EMF is really powerful. It gives us metrics, it gives us that structured logging that we're going to use in the future. And you'll see we're going to use EMF in that format repeatedly throughout all of these invocation types to log the errors, the service, etc., that's having the problem. In the synchronous case, the middleware is then going to inspect the error that it caught. If it's one of those custom errors or something that the client should be aware of, it can return successfully from the Lambda function. And when I say return successfully, the Lambda function still completes. It's not going to throw an error, but it's going to return with an erroneous status code, again, maybe 404 in the case of a record not being found, with a useful error message for the client. If it's any other type of error, something that's happening on the back end that the client can't recover from, we're going to want to fail that Lambda invocation by throwing or raising an exception. Let's take a look at how to implement that in Python. Now, while I've implemented this in Python for the talk today, you could implement this type of approach using any of the runtimes that Lambda supports. For our synchronous implementation, and actually all of the different invocation types, we're using an open source project called AWS Lambda Power Tools. And Power Tools is a suite of utilities for Lambda functions that makes it easy to adopt best practices such as tracing, structured logging, and custom metrics. It also gives us the ability to define our own custom middleware, and that's what we're doing here. So you'll see at the top of the code sample, we have our function handler. It's really pretty simple, but it also has a decorator, that @error handler just above it, that ties it with the middleware down below. But in the function handler, we're going to go perform that find book operation. If no results come back from the database, we can raise a book not found error with a little bit of detail about what happened. Otherwise, return with a successful status code and the JSON payload that shows what that book looks like. In the error handler itself, we're first going to instantiate a Power Tools logger, which gives us a lot of extra goodness and detail out of the box already. But then we're basically wrapping a big try catch block around the function handler itself, so that if any exceptions are thrown, we're going to catch it. We're going to log that exception using the Power Tools logger. And then we're going to again take a look at what error was actually thrown. If it's a 400 or client type error, we can again return successfully with a status code of something like 404 again, and a body containing the error message. But if it's an actual failure of the function, we want to raise a useful exception that we can then log and our developers can diagnose. That difference between returning successfully from your function and failing the invocation of the function makes a big difference when we talk about tracing. So this is an example using AWS X-Ray, where I have 3 different functions fronted by Amazon API Gateway. The function that you see at the top of the service map always fails. It always raises an exception. And you can see it's kind of notated as failing with that yellow circle all the way around it. The other 2 functions, one of them fails about 50% of the time because the book that it's looking for isn't in the database. Now you'll see though that it always has that green circle around it, which means that the function is still completing successfully. But once you reach API Gateway, you'll notice that about 50% of the time, the API is returning successfully with a 200 type status code. About 25% of the time it's yellow, which means it's a warning and a client type error. And the other 25% are server-side errors, and those are red. And API Gateway will generally return something like internal server error in that case. So by returning properly from our Lambda function, we can get really useful traces out of tools like X-Ray. One thing to note for the Node.js fans out there, if you implement your Node.js function with an asynchronous handler, you'll want to use a promise rejection in the case of the function failing, so that it shows up properly in the trace, as opposed to just raising an exception. Next, let's talk about asynchronous invocations. In our eCommerce example, this was EventBridge publishing to a message, but Amazon SNS and Amazon S3 are also very popular asynchronous event sources. If your Lambda function fails while processing an asynchronous event, the Lambda service will automatically retry 2 times. Now you are charged for those additional 2 times as additional invocations of your function, but it does try to retry the failure automatically. Now you do have a couple options here to change that behavior. First, you can use the maximum retry attempts configuration to lower the number of times that the function will automatically be retried, down to 0 or 1 retries. You can also set the maximum event age. So if you only want to retry an event if it was less than 15 seconds, you could do that as well. So you have some flexibility here in terms of how often your function is going to automatically retry. Now, if the event source fails to deliver to the Lambda service, or for some reason your function gets throttled, the event source will retry publishing that message over hours to even days using exponential backoff. So it's very important to understand the error behavior and how the system retries to avoid having a lot of unnecessary invokes of your function. Now, asynchronous invocation gives us an additional tool in the toolbox that we didn't have for synchronous invocations. And that's a feature called Lambda Destinations that was released at reInvent 2019. Essentially what we can do with destinations is route the result of a function execution, whether it be successful or in our case a failure, automatically to an Amazon SNS topic, an SQS queue, an EventBridge event bus, or even another Lambda function without any additional code. And the payload that gets routed to that destination includes not just the original event or the original payload, but also some additional metadata, like the number of retry attempts, the function name, etc. Now, when you go to configure your Lambda destination, you can use something like AWS SAM, as we're showing on the screen, and you actually configure that destination as a property of the serverless function. That's important to note because a little later in the talk, we're going to configure another destination, but we have to configure it in a different way. All right, so how do we handle errors in the asynchronous invocation? In your function itself, generally, just throw the error. Let the middleware handle it. If your function does call some downstream service, you might want to consider implementing a retry logic or some sort of circuit breaker pattern. But in most cases, throwing the error is just fine. In the middleware, we want to catch all the errors again, log the errors again to CloudWatch using EMF, and then re-raise the error so that the function fails. And by re-raising, after you've reached the maximum number of retries, that event will be published to your on-failure destination. again, with the original event data and some additional metadata. The implementation actually looks very similar. Again, we're using AWS Lambda Power Tools to build some middleware. Here we're showing you how to add some additional detail to what messages get logged to CloudWatch by adding the Lambda context. And we're also showing how you could potentially break out different types of errors. Here we're breaking out AWS service errors from the Bodo framework and handling them slightly differently than we would just any other generalized exception. Next, let's talk about the first of our pull-based invocations, streaming event sources like DynamoDB streams or Kinesis. Now in these cases, there's messages sitting on a stream, and the Lambda service will keep retrying as long as those messages are sitting in the stream if the function fails. But again, it's important to remember here that these messages are delivered in batches of messages. It's not just one, it's generally a batch. Now you can control which messages get published in that batch using the maximum record age and maximum retry attempts, which are similar to what you'd expect based on the asynchronous invocation of similar name. But there's also a feature here called bisect batch on function error. And essentially what that does is it starts to have the batch and invoke the function again on that half each time the batch fails. And eventually, as we have and have and have, you'll get down to just the one or small number of records in the batch that are failing being processed on their own and successfully processed events being successfully processed. Now, if you do choose to use that bisect on batch type approach, it's important that your function be idempotent, which means it can run multiple times successfully without additional side effects. So bisect on batch is a very powerful feature, but it's important to understand what it means. That also does increase your function invocations, but it's not counted toward the retry limit. The handling in this case is very similar to our asynchronous invocation. We're going to throw errors, we're going to catch them in the middleware, log them, and re-raise the error. We also have access to Lambda Destinations here. So we're going to send any failing message to an on-failure destination. But there's two things that are important to note here. First, your on-failure destinations can only be an SQS queue or an SNS topic in this case. And that destination does not receive the original payload. Instead, it receives metadata about the stream itself. And you can use that metadata to then go look up the batch of records that failed in the future. But if you're just trying to process the events that show up in your failure queue, for example, the same way you would with an asynchronous invocation, it's not going to work that way. You have to go look up that batch on the stream again. Now here's one I learned the hard way. When you go to configure your destination for a streaming source, you actually configure that destination on the stream itself, not the function. So you can see that here in this AWS SAM template, we have a destination config associated with our DynamoDB stream, not with the function itself. Our second pull-based invocation type is for SQS. Now again, we've broken SQS out from streaming event sources because the approach to handling errors and the configuration options available are different. Like the streaming event source, SQS delivers messages in batches to your Lambda functions, and those messages are going to be retried automatically by the Lambda service for as long as the message is on the queue. Now, the one major thing that's different here is that when messages are successfully processed in that batch, your Lambda function could actually go and delete that message from the queue so that it's not included in a future batch. But again, the default retry behavior is to automatically retry for as long as the message is on the queue. You do have some configuration options here, like using dead letter queues, either for the Lambda function itself or for your queue, SQS queue. You also have control of the batch size from one message all the way up to 10 records in a single batch. We recently also introduced a batch window size for a time-based batch. You can control the visibility timeout on the queue itself. Our approach to handling errors in this case is a little bit more complex than the others that we've already talked about. Now in this case, what I would recommend is in your Lambda function, have a separate record handler or another method that can process each record in the batch individually. When those records are processed successfully, great. But if there's an error, catch any of those errors in that record handler method, and then return it as a group, the successfully processed ones, the erroneous ones, to your middleware. Your middleware can look at the results of the entire batch. If there are no errors, the middleware can simply return. And in that case, the Lambda service will actually go and remove all of the messages in that batch from the SQS queue. It's really powerful and simple. But if there is an error, the middleware should actually iterate through the results, delete the messages from the queue that were successfully processed, and then raise an error indicating that there are some erroneous messages left in the batch. Now, you might choose to let your function reprocess those or immediately move them to a dead letter queue. That's up to you based on your business needs. Now, that sounds a little bit complex. It's not terribly hard to implement, but the really good news is that some projects like Lambda Power Tools gives you the ability to handle partial failures when processing batches of messages from SQS event sources. This is a really simple example that demonstrates how to do that using Lambda Power Tools in Python. This is also available in the Java version of Power Tools. And there's also a readily available plugin for MIDI.js that you can use to implement the exact same approach to handling errors in SQS records or batches of records without having to implement too much on your own. So it's been done in a lot of cases, and it makes it a lot easier and more efficient to handle batches of messages from SQS when there are errors. Let's also talk about step functions before we finish up today. As I mentioned earlier, step functions is incredibly powerful, very configurable, and we can define the retry behavior as well as error handling right within the state machine itself. I could even go and implement a centralized error handler right within the state machine definition as well. So I can get consistency right within the state machine. And we can customize this to meet the business needs of the complex process that you're orchestrating with your state machine. Let's look at a simple example. So here we have a pretty simple state machine. It has a task called call API, which invokes some Lambda function. And if you look at the JSON on the left, you'll actually see that we've implemented the retry behavior and a try-catch type logic right within the state machine definition. So if that Lambda function returns an error of too many requests exception, the state machine will automatically retry that step or that task up to 2 more times with a 1-second interval in between. So your retry behavior is defined right within the state machine. The developer of the function doesn't need to know anything about it. Now, after that maximum number of attempts, or if another error occurs in the function, it'll actually bubble down into that catch block. And here you can see, if we have exceeded the maximum number of attempts for too many requests exception, it'll move over to a wait and try later state and presumably try again. If there's another error that occurs, like server unavailable exception, it'll move to another state in the state machine. Or if there's an error that occurs that we haven't explicitly named, we can catch it using something called states.all, which basically catches any other errors that might occur so that we can handle them. Again, step functions gives you a lot of flexibility and configurability here to build in the retry logic and the try-catch type logic that makes sense for your state machine. We've spent a lot of time logging today. We talked about logging for pretty much every invocation type. So what does that do for us? It gives us more visibility into our errors. So by using CloudWatch embedded metric format, you'll get metrics out of that. And you can actually build dashboards and alarms off of those metrics. Because these are structured log messages, you can also see in the screenshot on the right, we can do things like run a query in CloudWatch Logs Insights to go find all of the error messages in a given time period for our developers to help dive in and try to figure out what went wrong. And of course, by returning properly from our Lambda function, we can use tools like AWS X-Ray to trace a distributed system and understand what's happening, find the failures. Now, of course, all of this is just a start. This gives you a lot more insight into your errors, you're handling them more consistently, But again, you can also go build things like CloudWatch dashboards, alarms, so that service owners are aware of errors exceeding some threshold. You can also use techniques like chaos engineering to go generate those errors to ensure that your error handling is as you want it to be. So I'd like to thank you for taking the time to listen to our talk today. We do have some other resources and documentation available to you on Serverless Land, and there's a short code link there as well as a QR code that you can use to access that information. So again, thank you. Please do take a moment to fill out the session survey. We really value your feedback. Thanks and have a good day.